My name is Rick Schwartz, and I'm the AP Tools Product Manager from Qualcomm Technologies in San Diego. And today we're going to be talking about lowering the power consumption of your application without affecting performance. A lot of the examples I'm using will be on Android apps, but the concepts we'll be discussing, problems and solutions apply to other platforms as well. In fact, all the hardware profiling techniques apply to any device with a battery. So, jumping right in, I was surprised to find how many popular apps do not use the processor, cellular radio, and other system resources efficiently. This wastes power and has a negative effect on battery life. It's surprisingly easy to measure power consumption, which is why it's a surprise that so few developers do it. And of course, if you can measure it, you can act on it. There's some very simple solutions to common power problems, and if you follow these, you're going to have better battery life and hopefully happier users. It's no surprise that battery life is the single biggest thing that consumers care about. It doesn't matter whether you're on Windows, iOS, Android. It's more important than screen size, more important than operating system. One of the reasons why it's such a challenge is we've seen a dramatic difference in the hardware specifications in the last 2 years. 3 years ago, flagship devices had dual-core processors. Today, a lot of them have 8-core processors. 3 years ago, displays were 720p. Now, a lot of them are 2.5K panels. 3 years ago, 720 or 1080 video was state-of-the-art. Now there's a lot of devices that do 4K video. And of course, during the same time, we've seen devices getting thinner and thinner and thinner, which leaves less room for a battery. And we've seen absolutely no significant changes in battery technology over the last 3 years. So where does the power go? What's the number one biggest consumer of power in a mobile device? It doesn't matter what kind of device, it's always your screen. You can see here on maximum brightness, about 1,600 milliwatts, that's 1.6 watts. Significant amount of power being consumed. Number two is the processor, although you can see it's very frequency dependent. At the lower frequencies, CPU is actually very efficient, and that's where it sits most of the time. Number three is a surprise to most people, the cellular radio. If you're transmitting data over 4G, it does consume about 1.3 watts, at least according to this data, which came from Android. 4, video decode. 5 was a surprise to me, Wi-Fi scanning. And then 6, GPS fixes, which is something that apps do more often than they probably should. So if you're wondering where you can get data like this on any phone, at least any Android phone, you can download the slides and click on that link, and it will tell you a bunch of information. If you want to find this data on your device, there's a path there. It's just an XML file you can access. Of course, there's an app for this as well. It shows the data in current, but of course you can easily convert it to power if you want. So how much power does your app consume? How many people have power profiled their app? Exactly 0. How many people have performance profiled their app? Okay, I would have hoped more, but it's surprising. Once you learn how easy it is to do this, I think hopefully you do it, and if you do, hopefully you find some benefit. I think the problem is most developers just don't know how to do it. So let's talk about how to do it at least. I'm going to give you an example on Android. If you're on other platforms, you'll find similar software, but Qualcomm makes a tool called Trippin. It's in Google Play. It's free. And basically, there's 3 steps. You select battery power. It's important you keep the processor awake if you want to get an accurate average. And then you decide if you want to profile the app or the system. What you're going to end up with is a graph, which you can see in the center, or kind of a stats view that shows instantaneous and average power. Any guesses why the power is a little higher than expected here? It's because we're running on target. Anytime you measure on target, you're consuming CPU cycles. We're collecting a lot of data. and that's going to draw power in itself. So you want to factor that into the readings, but it's something to be aware of. There's a lot of other good software options available. I've listed a couple here on Android. Of course, they're on every platform. GameBench is a really good app. GSAM Battery Monitor Pro. Power Tutor does per rail modeling, worth checking out. As I said, if you can measure it, you can act on it. What I typically do is I'll first of all measure the power when a device is idle. And I'll do that with the screen on and off. That way I can kind of back out the screen power, which is typically something a developer can't do too much about. Next, I'll launch the app I want to measure, and I'll look at the average power idle. You think there wouldn't be a difference between that and the idle device power, but oftentimes there is. And then, of course, the important thing is you want to do actual real-world use cases. One thing I like to do is I use software that will kind of record my taps so I can reproduce the same kind of use case on different apps, because it's very helpful. Let's say you're a game developer and you're making a driving game. You're going to want to compare your game to the other kind of leading apps in that category. It doesn't do any good to compare your app to a social media app because you're going to have very different expectations. And then as developers, it's very easy if you can measure power to try different things, and then you can see if it makes a difference. I'll give you some examples. In fact, one way to tell if you're making a difference is to put markers in your code. Here's an example on Android with the Trepin app, but you can use the same technique with other applications as well. Basically, what the script is doing here, I'm just numbering the intent. I'm naming the intent. Then you run your app. Every time it changes states, you'll see this blue line change, so you can tell where you are, and then you can look for the power spikes. Sometimes the raw power is a little bit almost kind of random looking, so it's helpful to look at a statistical view of the averages. You can see the first intent here is loading a web page. It shows that it's drawing 1100 milliwatts. Then we scroll the page. Then we pause scrolling. You can see a significant drop in power. We load another web page. You can tell these pages are very different. The second page is a lot more efficient, and you can see a big difference in power consumption. So even as a website developer, there's ways that you can compare your page to other pages in terms of the actual power that is required to load that page. I find it's helpful sometimes when you zoom out, when you zoom way in, you just see what looks like a bunch of noise. When I zoom out here, I've selected 2 data points. Battery power, it's hard to tell on this screen, but battery power is blue. In fact, you can see it here. And then the purple line, which looks pretty similar on this screen, is actually the GPU load. So you can see there's a very strong correlation here. I'm running a graphic benchmark. So it goes between 0 GPU load and almost 100%. And on the spikes, you'll see the battery power is very highly correlated there. So how accurate is it? To determine the answer to that question, I ran a script where I forced the brightness at different levels from 20 to 100%. I used a piece of hardware power measurement called a monsoon power monitor, which is something that's very popular. And then on the same device, I ran on-target software power measurement, the Trepin tool we've been talking about. And then I kind of plotted the difference, and you can see it's actually very accurate. In fact, it's probably even more accurate than we show here, because what I did on the monsoon is I selected my average power. When you use ADB over Wi-Fi, it creates some spikes, and I kind of took my averages after the spike. So that's part of the difference we're seeing. But bottom line, it's extremely accurate. Here's an example of a script like I did. Mine was for screen brightness, but here's one for processor frequency. You can study the slides if you're curious. It's important that you set the duration for a minimum of 30 to 60 seconds if you want to get a good, accurate average. So you're going to see it's actually pretty helpful in terms of some comparing different things. So on the left, I was doing a 4K video playback using a software decoder. On the right, I'm using a hardware decoder. The green line is CPU load. You can see it's pretty much maxed out on the left, 80 to 100%. On the right, the average is 31%, so that's about a third the CPU load, and about 43% less power, so pretty significant difference. Just to summarize, so far everything we've been talking about is software power measurement. Hardware is very important as well. The reason I like to start with software is it's so easy. You can download a free app. You don't have to spend $800 on a piece of equipment. And more importantly, you don't have to modify your device. A lot of the flagship phones nowadays don't have removable batteries, which means you're going to have to tear open that device. You're going to have to break the battery connection, and something you may not want to do with a very expensive phone. My biggest advantage of software power measurement is you don't have to be tethered. So you can use your phone just like normal. You can run it. In fact, sometimes I'll just let it run for 24 hours. You won't notice it. And then you can go and analyze the data after the fact. And you'll see some very interesting results. So that's going to show you things like Wi-Fi scanning. It's going to show you a handover from Wi-Fi to cellular connections. It'll show you what happens when your signal strength drops on a cellular connection. Very revealing. It also shows you what's happening when your device is idle, which is very shocking once you see that. Another advantage of software, you can do per rail power measurements of hardware blocks. Let's say you want to see exactly how much power the GPU is using, or you want to port code to run on the CPU to the GPU. You want to see how much power you're saving, or you want to port it to run on a DSP. You want to see the difference. You can do all that. The downside is not every device supports direct power measurement. And of course, you're on target. That's the big one. So you are influencing the power measurements. If you want your most accurate measurements, you're going to use hardware. And also, there's some really nice graphing that you're going to get. And another significant advantage is hardware is a higher sampling rate. So for example, a monsoon samples at 5,000 samples a second versus software like Trepin that samples at 100 samples a second. So those are some of the pros and cons of each. They both have their place. We talked about per rail, something that is a nice advantage. Of course, you can do it with hardware too, but it's much more difficult to do. So here's just an example. You're going to find that each chipset company has their own development hardware. I'll use Qualcomm as an example here, just so I can give you some specifics. If you take a Snapdragon 810 tablet, it's going to give you the power separately for the CPU cores, the big cores, the little cores, the GPU, the backlight, front and rear camera, system memory, SD card, Wi-Fi, sensors, USB, about anything you'd want. Does it work? Well, here's a test. I've got it set for delta, so it's going to show me the difference between the baseline power, which is here, and then I start profiling. So the delta between the baseline and the current power is 0 for the CPU and the camera and the graphics and the internal memory. In other words, I'm not consuming anything separate. Once I take my photo, you'll see a big difference. The CPU goes from 0 to 651 milliwatts. Camera goes from 0 to 53 milliwatts, gives you an idea of the difference in kind of the power used. The memory goes from 0 to 126 milliwatts. Depending on SD card is showing 0, but if I had sampled at a different point, we would have seen that go up as well. So there is a pretty strong correlation between things that you would expect to happen. The reason for the difference in LCD backlight is one of the screens was almost all black, and the other screen was almost all white. So it's going to make a difference in the power. So it's very sensitive. If you want to go the hardware route, there's three ways. The easy way is just to take out your removable battery if you're lucky enough to have a phone like that. Just attach some mini grabber cables and away you go. If you want a more accurate method, this is going to be accurate, but if you want to have the fuel gauge work and the battery temperature sensor, then you're going to have to use flat insulated copper tape and break the battery connector, and it's a little bit of work. And then, of course, if you're lucky enough to have an iPhone 6 or a Galaxy S6 or a Nexus 6 with a non-removable battery, you're going to be ordering some special screwdrivers and breaking your device apart. And in this case, I took it to our proto lab because I was lazy and had them do the modification. But it's not much fun, and you're pretty much ruining your device. But it is nice to get the accurate power. Some best practices that apply to both hardware and software measurement. A lot of people don't realize you're going to have to remove the USB cable. Of course, if you're an Android developer or iOS, you're going to want to keep that because you're sending data and you're using ADB in a lot of examples to script. But you can't do that because you're charging the device. It's going to influence the power readings. So what I do is use ADB over Wi-Fi. Things like Monsoon have an auto mode that will kind of break the power connection on USB if you want to do that. Make sure the CPU and the device capturing the power stays awake. So if you're using a Monsoon, make sure your computer doesn't go to sleep or you're going to get some data that is going to drop out. Same with the mobile device. I showed you how to do that in the earlier slide. You want to minimize the background processes. It's crazy how much stuff is running on Android or iOS in the background. And it makes a big difference. I did a test, and I found about a 30% delta in power between when I closed everything, every unneeded service and app, and when I just kind of let the device run in its kind of standard mode. I like to use on Android Nexus devices because they have a lot less things running in the background than some of the carrier devices. You want to turn off everything that's not related to what you're measuring. So a lot of times I'll go into airplane mode, turn off. If you don't need GPS and Bluetooth and all that, turn it off. Minimize the impact of the screen. Typically, I'll drop it down to minimum brightness. Sometimes, if I'm doing idle power, I'll just turn off the screen. And then there's a whole list of best practices. If you download the slides, you'll see a very, very long list of other helpful features. So the reason you're here, I guess, is to determine, does your app have a problem? And it's very easy to tell. But the first thing I guess you got to know is, what are the top problems? And I find that it doesn't matter what your OS is, you've got the same 5 problems on every platform, really. Number 1 is inefficient use of the cellular radio network and Wi-Fi. 2 is preventing the processor from going to sleep, very common problem. Almost every app does it. 3 used to be a big problem, but we don't see it too much anymore, keeping the display lit too long. There are some very famous games that still do that. It's called a full Wakelock, and they do it, even though it's very easy to avoid that. 4, another big problem, not using all the available system resources. One of my pet peeves is taking too much GPS fixes. Every time I launch the Twitter app, the first thing I see is it does a GPS fix. Even though I'm not tweeting, there's no real reason it has to do that. It's just wasting power for no reason. Okay, so does your app use the radio efficiently? Things like social media, in fact, most apps are pulling notifications more than they need to. And the reason this is a big problem is if you'll look at the way a cellular radio works, when it's idle, the power consumption is very low. This says 10 to 12 milliamps. I've seen even a modern device probably lower than that. When it goes into a full power transmitting mode, you're going to see a big spike. This chart is an older device, probably a 3G device. It says 250 to 350. You'll see later it's actually higher than that. When it's not sending data, the radio drops down to an idle state, but it's still using a significant amount of power in that state, and it remains there for 8 to 15 seconds. That's what's called the cellular long tail. And then, of course, finally it drops back down. So the best app I've seen that kind of gives you a visual representation of this is something that ATT makes called Arrow. It's a free download, and it's really a nice app. You can see the actual packets sent on those top lines. The kind of ramp up on the red is the cellular radio going into a full power transmit state. Stays there transmitting for 4 seconds. In this case, they don't close the connection, so it has to just time out after another, looks like 5 seconds. And then after that, it takes, looks like another 10 seconds to actually go back to that idle state we talked about. So that's all wasted energy. There's a bunch of other things you can do with Arrow. It's going to show a lot of other problems, and you can read about that. My favorite thing is it will run a kind of suite of 25 different tests on your app, and gives you a very simple report where you get kind of, green checks or you get a red X. And then you look at the problem areas, and when you click on that, in this case, there's a connection closing problem. It tells you what the problem is. You can click on Learn More, and it will give you some best practices how to eliminate that problem. A very useful app. This is an interesting test. You'll see a lot of theoretical charts. I wanted to actually plot real data on a real commercial device using free software that everyone in this room can get. So I took my Nexus 7, and I went to Google Drive, and I launched Trepin. I opened a folder, I opened a document, and you can see the result here. So I put some red lines so you can see the correlation. Here's the mobile data state. We start in idle. Here's where I open my Google Drive folder. We go into a full power state, and you can see the power increase there is about 800 milliwatts, significant amount of power. Later on, it drops back to idle, but almost immediately after that, I clicked again and opened a document. You can see similar thing. So it drops back 800 milliwatts, and then it actually goes up 1,200 because I was loading a document. There's probably more data being transmitted. This is the interesting part here. Here's kind of the long tail, where we go from the full power state finally down to this dormant state. And then here we have data right after that. So this is better to actually see what happens. So if you'll look at the marker numbers, actually 7, I think I've got it wrong. The radio goes from an idle to a dormant state, and the power decreases 600 milliwatts. So it just shows kind of the theoretical chart earlier that it really exists. And in fact, the numbers are bigger than people think they are. So it's very important that you close your connections, and you want to minimize, you want to group your traffic to minimize the inefficient use of the radio. There's other apps. Here's a plugin for Eclipse if you're an Android developer. And this not only plots all your cellular states, it also plots the correlation between CPU, GPU. You can see display brightness, you can see GPS. And then you can go through and actually click on and see all the different data, because it's nice to actually correlate the data. Is there a reason that the processor is being kept awake? Maybe there is. Maybe there should be. Is there a reason an app's transmitting data? Or is it just doing something, is just analytics or something that is just kind of phoning home when it doesn't need to? And you want to launch this, you want to look at your app and see if you see any problems. I was messing around. I just set my phone on my desk, didn't do anything for 3,500 seconds, whatever that is. And I was very surprised to find out that my phone was very busy, even though there wasn't a single app launched. In fact, you'll see at most of the time, 2 of the cores are active. A good percentage of the time, I got all 4 cores active. You can see the GPU is active 4 times. GPS, 3 times, probably analytics. The radio was going almost a continuous time. And then a lot of data for an idle device. So there's a lot of apps that have problems. I was really curious to know, what is all that data? So I started messing around, and I saw in the list Google. So I thought, well, let me turn off Google now and see if it makes a difference. I turned it off, did the same test, and I saw, wow, a big difference there. I suspect it was the always listening feature in Google, where you say, okay, Google, and it wakes up. There's a price to be paid of things like that. So how do you efficiently use the radio? You want to connect less often. As we said, after you transmit, the radio is going to stay on for at least 10 seconds. Push, don't pull. Send packets, wait to see if they respond. If you're on Android, you want to use things like Google Cloud Messaging. Don't continually scan. Create timeouts when scanning Wi-Fi networks, GPS signals. I was here earlier, and I noticed an app was trying to get a GPS fix, and it couldn't get one for whatever reason. No satellites, who knows? And so I set a little timer on my phone, and it continued for 6 minutes, and it probably would have continued indefinitely. A huge waste of power, and it's so easy to avoid. As a consumer, I like ad-free versions of apps because in the long run, you're gonna pay less for a paid app than a free app. And then analytics, something that's very helpful. I love analytics on my app, but there's a price to be paid. And if you do your homework, you'll find there's a big difference between different analytics. You can see some of the differences here, and of course, you can do some online research and do your own. One thing I've been playing with lately, there's some good sites like MixRank, where you can type in any app, doesn't matter if it's Android or iOS, or in fact, you can go to any website. So just for fun, I typed in the BBC News app and the BBC website. I found the BBC News app used 23 different SDKs. It's pretty interesting to see what they are using. It's also very interesting to see what they stopped using. And then you can look at other popular apps, and if you see, oh, well, why is everyone dropping this SDK? Well, there's probably a good reason. The BBC website actually uses 38 different SDKs, so follow the leaders, see what they're using. Sometimes you can save some time. Don't continually stream, download in chunks. You can either manually group your traffic intelligently, or you can use, if you're on Android, you can use something called the Job Scheduler API. And you can see a difference here where this red line is the mobile data, all these little separate bursts. And if you group them, you're going to find that it's a lot prettier to look at. And of course, the radio is going to stay on a lot less. So here's I got 3 different apps sending data. If we group them together, the radio, it has to transmit a little longer, but compared to the total time of the 3 separate transmissions, you're going to save a significant amount of power. In fact, up to 50% the power. If you're an Android developer, there was something they launched last year called Battery Historian. It's actually a pretty useful app if you want to see wake locks, if you're keeping the processor awake, if you want to see what's happening with syncing and the cellular radio. It's very easy to install and run. You can see the script commands. You could do this in 5 minutes. And I will show you what a plot looks like if my computer will cooperate. Let's see here. So it will show you the battery level. Every time you see a line, so I start at 97%, each line is a drop of 1%. And then here's the screen. So you can see when the screen's active, for here it's 13 minutes, you can see the battery kind of drops at a much faster rate. Here it's active for 30 minutes, significant drops. So I went from 97% to what did I start at, 97? Yeah, and already I'm at 76% battery. So you can really see the correlation. I'm not going to go through all this, but you can see how much syncing is done. Here's effectively when I went to bed, and it basically syncs all night. There's different things going on. This line is wake locks. These are apps waking up the processor, happening all night long. Fortunately, Android just announced a new feature called Doze, which is hopefully going to improve that, which is a good thing because it's a huge problem. You can look at this yourself with your own data. There were a couple surprises for me. One, I was surprised that the Wi-Fi radio scans continuously. It's only for 4 seconds, but it happens every hour, so that's interesting. I'm not sure if it has to do that when you're sleeping, but it still does. So a lot of interesting information, and I encourage that you, if you're an Android developer, you check that out. Moving on. wrapping up how to efficiently use the cellular radio, wait for the right connection. Another problem that many apps have, they don't wait until you're on Wi-Fi. The Microsoft OneDrive app actually gives you an option to wait until you're charging, which is something I wish more apps did. It makes a lot of sense. So why is this such a big deal, waiting for Wi-Fi? Before I left, I was in the office, and for some reason I had Wi-Fi turned on, and I was surprised that Android said, hey, do you want to update these 4 apps? And I thought, well, that's strange. Why would you ask me to update 4 apps when I'm on a cellular connection? So just for fun, I connected up my Monsoon. I clicked on Update Now, and I did a quick test here. So I found that before I started downloading, my device was using 700 milliwatts. From point A to point B, when the radio's mostly active, I see a jump to 3,279 milliwatts, a delta of 2.5 watts. For fun, I did a download test over Wi-Fi and found that it uses less than half the power. My estimated battery life dropped from 15.8 hours to 5 hours. I wasted 70 megabytes of my data. And wasted 11 minutes of my time. So here's something that a developer, you think if anyone would know, Google would hopefully do that, but it's something that any app can do. It's very easy to do on any operating system. Just wait for the right connection, and you'll save the user a lot of frustration and data and time and more importantly, battery power. Does your app keep the processor awake? Doesn't matter what platform you're on, you'll find there's apps available. On Android, there's a good one called Wakelock Detector. Battery Historian is also very good for showing wake locks. You want to look at the duration of wake locks. A lot of developers don't look at the number of wake locks. Even though a short wake lock seems less damaging, if you have enough of them, you're going to waste a lot of power. You can see some stats on the right. If you're an Android developer, a lot of developers don't know if you go to Settings Battery and select an app, you can see some really, really useful information. And here's an example where I was using turn-by-turn navigation. So I was in my car for 30 minutes, and of course the GPS is active almost all the time. But here's the important stat. The CPU was in the foreground 19 minutes. So even though the numbers look big, actually, there's nothing to be alarmed there. This is the type of thing you want to watch for, and you can just pretend that there's no names at the top, but I found it was useful to have real apps. In fact, they're all very famous, popular apps. Here's a popular travel app. I didn't use it at all. It was never in the foreground, but it kept my processor awake 4 minutes, kept the GPS active for 12 minutes, almost as long as turn-by-turn directions. So basically, it was constantly doing GPS fixes for no reason. Wasted some mobile data, even though I was on Wi-Fi. Don't know how it did that or why. You can see some other kind of examples there. So don't keep the processor awake. If an app's not in the foreground, you want to certainly be respectful of the environment. It's very easy to do. These are some examples for Android, but you'll find similar examples for other iOS, for other mobile OS. Don't acquire power manager wake locks. Use the minimum levels if you do. Release them as soon as possible. You want to use alarm manager where you want to have the application run at a specific time. Android's now handling that more efficient, and there's some better techniques for timeouts like Handler. Does your app use the display in a power-efficient manner? Full wake locks, I mentioned there's a very popular game that always keeps the screen awake no matter what. If you want to keep the display lit, you want to use a flag keep screen on instead. It's going to have a significant impact on power. There's a direct correlation between brightness and power consumption. I did a test here. You can see. This is a big surprise. Offer dark theme options. It doesn't matter what platform you're on. I took the Google News and Weather app, and in fact, it's not even a black background. It's a mostly gray background versus a white background. And I found that the light theme used 893 milliwatts, the dark theme used 410 milliwatts. Huge difference. Something that's easy for you to do, and your users will appreciate it. Does your app use available system resources? There's a bunch of different apps that will tell you this. You want to look at your CPU load. Obviously, if you're at 100% all the time and there's not a good reason, like running a benchmark, that's a problem. You want to look at whether you're CPU or GPU bound. There's a lot of good profiling tools that will show you that. You want to make sure, you want to be aware whether you're using all the cores efficiently. Most apps, even benchmarks, don't really use the last 2 cores of a quad-core processor. And there's some software that I'll talk about later that'll help you to spread your load over the cores more efficiently. In fact, heterogeneous computing is something you're going to hear about a lot more if you haven't heard about it already, and that is running the right task on the right engine. Things like browsing and game AI are best on the CPU. Things like audio, object detection run really well on DSP. You're going to save power. In fact, you save about 30% more power. And then, of course, there's a lot of different tasks that run best on the GPU. This is one example of a developer programming library that will help you do this. Of course, there's many others examples out there. So how do you save power by offloading to DSP? If you're on a platform with a processor that has a DSP, the benefits are huge. Here's 3 examples. Playing audio over DSP is going to extend your playback time to 60 hours. That's a 50% increase. I've got a wearable, and I use it for sleep tracking. When you use the DSP for sensor batching, 8 hours of sleep trapping only uses 10 to 20% of battery life. In fact, my example is even better. I basically wear my watch 23 hours. I wake up, I charge it when I'm getting ready. It charges for about an hour, and then I go through the same cycle again, the 23-hour cycle. It never runs out of power, and the reason is it's using the DSP for sensor batching. It's easy to do. And then, of course, things like facial detection are going to run faster and use less power. Those are just 3 of many examples. Does your app take too many GPS fixes? It's easy to determine that. Don't take one if it's not needed. Uses coarse GPX fixes when possible. Again, this is a random screen capture, but some very popular apps that will tell you if the battery usage is high. And that's an indication that they're not using coarse GPS fixes. Let Location Manager find the best provider. Use a timeout if you can't find a satellite. Many apps don't do that. Disable GPS when the app's asleep. Most apps don't do that. And then as a user, I like it when people give me the choice to disable location without crippling an app. Of course, performance matters as well. It's no good to save power if you're going to affect your performance. So you want to run software. There's a lot of good tools out there. These ARM Streamline, Intel has an Indie suite of tools. GameBench is one of my favorites. It will show your frames per second, which is a great indication whether you're affecting the performance. So as you're trying these different techniques we've talked about, you want to make sure that your performance hasn't dropped. In most cases, it won't. So just to kind of recap, use wake locks only when necessary. You don't want to keep the processor awake. Close your sockets when done. Otherwise, you're going to bring up the network just to tear it down. That can save a lot of power. Group your network activity. You can do it manually, or if you're on Android, you can use the API I talked about. There's a couple recommendations at the end that came from our graphics group that apply to game developers. One tip is optimize your app to run at 60 frames, but then frame limit it to a lower rate. This cuts GPU, CPU, memory utilization by 50%. Avoid rendering at full native resolutions. That'll save your GPU power. So the bottom line, long battery life is very important to consumers. There's really no excuse for bad power management. Free software is available, makes it easy to locate and fix problems. and better battery life is going to give your app an advantage over the competition. So I've got a bunch of useful links that if you're interested you can check out. There's some really good videos online. You can check those out if you're interested. And I've got a couple minutes for questions. I apologize for going so fast, but I wanted to make sure I didn't run out of time. Any questions? Yes.
What does DSP stand for?
Sure. Digital Signal Processor. A lot of the popular chips either have on the SoC, they'll have a floating point DSP chip, which is very good for things like audio or image detection. Other platforms like Apple will use a microcontroller that's not part of the SoC, but it's still accessible in some cases, and you can offload things to it. Other question? Yes.
Can you talk a little bit about wearable devices, specifically using the DSP for sensor
Yeah.
selection and also the synchronization between the mobile device and the wearable device?
Yeah, there's some really good information out there. If you Google it, the app that I use is called Sleep as Android. If you Google sensor batching and wearables, I think you'll find some good information. The bottom line is you're going to wait until the CPU is awake. So you're going to batch the data. In most cases, like with a sleep app, it's looking at the gyroscope, and then you're waiting for the processor to be awake. And when it is awake, you say, "Oh, by the way, I've got some data." So in the case of my Android Wear device, the processor is basically almost never awake. So because I'm sleeping, it doesn't need to be, and it'll save a huge amount of power. In fact, there's some devices that don't have that feature, and when you wake up, the battery's going to be 100% dead. And the ones that do, you're going to wake up and find out that you only use 10 or 20%. But there's some good information if you Google that, more information on that topic. Wearables are still kind of in its infancy. It doesn't matter which one you're talking about. Right now, the power optimization is, it's been a rush to market. They want to get the devices out. In many cases, they're using, a lot more code on the device than they need to be. In many cases, they're using mobile processors that aren't really optimized for a wearable platform. We're going to see much more power-efficient monitors and power-efficient processors, and also OS that handle this in a better manner. So, yes, question in the back.
Do you have any idea how the style of how I do some stuff, like if I use random script or ADK or normal Java, influence my
I don't have any information here. It would be pretty easy for you to test for yourself. You can use software like we've talked about. You can also use some of the hardware tools. And we talked about putting markers in the code. So you could actually have a piece of code that used one technique, and then you could try the other technique. You don't even have to script it or stop your app. It's pretty easy to see the difference. If you look at the average power measurements, you'll probably see a difference there. Not in every case. You will find that there's a lot of background activity, so you're not just going to do one test. You always want to do 3 tests. If you see any really high numbers, you want to throw them out because you're going to be getting spikes that aren't really meaningful. So it's easy for you to do the test yourself. Time for 1 or 2 more questions. Thank you very much for coming. And if you want, you can download the slides. I appreciate you stopping by. All right.